Hello everyone. We are going to continue our lecture on probability, but in this section we are going to talk about joint and conditional probabilities. Now, whenever we say the word joint, it suggests or implies two things, correct? We can only join two things or maybe three things, but it has to be more than one thing. We cannot join just one thing. We always need two things to join them to make a connection between them. So here we are going to talk about situations with two variables and how they are connected and how to find probabilities in the case of joint variables. All right. So we are going to talk more about events that can occur together. Right. And then we are also going to talk about conditional probabilities, but we are going to go into the details as we move on. All right. In this section, we are going to cover the following topics. Number one is the contingency tables. Contingency tables are nothing but frequency tables, but frequency tables created for two variables together. All right. So we will go into the details of that and we'll talk about joint and marginal probability. And other words, we will learn how to read a contingency table. First of all, we create the contingency table and then we will be um, learning how to interpret the table and then how to create different kinds of probabilities from the table. Then we'll talk about conditional probability, which is a very important topic of probability and useful one too. And then independent events, what independent events are. Then we'll talk about the general multiplication rule and the special multiplication rule. Earlier, we had studied about the general addition rule and the general multiplication, and the special addition rule. Now we are going to talk about a couple of multiplication rules, right? We'll talk about the contingency table now, which is nothing but a frequency table, but with two variables in it, all right? Now, the example that we are going to use is create a contingency table for age and rank of faculty members. All right. So this table, the study is perhaps on age and rank. So there are two variables there. One is the age of faculty members at a certain institution, and then also the rank. So when we sent out the survey, or when they sent out the survey for the study, they had two questions in there. One of them was, what is your age? So they had to put their age down. And then what is your rank? So the different ranks here are full professor, associate professor, assistant professor, and instructor. Whereas the different age groups are under 30, 30 to 39, 40 to 49 years, 50 to 59 years, and 60 and over. And they have given some notations. Instead of saying full professor and associate professor each time, the events have been named as R1, R2, R3, R4, R standing for the ranks, and for the ages they have denoted them by as A1, A2, sub 2, A sub 3, A sub 4, and A sub 5, A standing for age. And over here we see a bunch of numbers, and then we see a bold rectangle box. Now what is inside the box are frequency values. Okay, you should be able to tell these are frequency values and not probability values. Probability values cannot be something like 170 or 57 or 2 or it can only be values between 0 and 1. Keep that in mind, all right? So this tells you this is a frequency table, and since we are working with two variables, age and rank, it's called a contingency table. All right? So inside the box, we have these values which tell us there are two full professors, or rather two people whose age is under 30 and who have the full professor rank. There are 156 individuals who are in the age group 40 to 49 and who have the rank of full professor. There are 163 individuals who are in the age group 30 to 39 and have the rank of assistant professor. So that is how you read the values in the center of this table, surrounded by the bold rectangle, right? Then another one, let's do another one. There are 36 members or 36 individuals who are assistant professors who are of the age 50 to 59. Okay, so these are all these values represent joint values because it describes each number describes two variables. One is the age and the other one is the rank. All right. Now these values, the total values on the last column, total values, as you can see, there are two totals. One is the column, so total, uh, the last column. This total is the sum total of all the rows of the individual rows. So 68 is the total of all those under age 30. 402 is the total of all those in the age group 30 to 39. 253 is the sum total of all those in the age group 50 to 59, irrespective of their rank. Okay, it doesn't matter whether the individual is full professor or associate professor, whatever the rank is. It just gives us the total of everybody who is in that age group. The total below in the last row represent the column totals, all right? So that means 430 represents in all individuals, regardless of their age, who hold a rank of full professor. So there are 430 full professors, doesn't matter what their age is. So this total value, the total columns and the total rows, they are marginal. They are not joint. All right. So when I say 68, 68 is the total of all those under 30. I don't even mention rank. So those totals are called marginal values. All right. These are the marginal amounts. And the ones in the center, these are values are the joint values. All right, all these values are the joint values, joint frequency values. Okay, and the total sample size is 1164. That's the sum of all the totals in the of the rows and the sum of all the columns add up to 1164, and both sides, the column as well as the totals along the last row, they should add up to the same value. All right, so 1164 is going to be what's called our N. Okay, that's the total sample size. All right, so I hope you understand. It's clear which ones are the marginal frequencies and which ones are the joint frequencies. Joint frequencies describe two variables together, and the marginal frequencies, and maybe amounts is not the right term here, we'll call it the marginal frequencies, represent the uh, the frequencies of a single variable, right? Either age or rank, but not together. All right. Now, earlier we talked about the joint and marginal frequency distributions. Now we are going to talk about the joint probability distribution. So this is a table here on the right and left hand side. These values here represent the joint probability distribution corresponding to age and rank of faculty members. All right, and in order to calculate the probability values, we will use the values in the of the frequency table of the contingency table, and I will show you how we come up with these numbers, probability numbers. Again, same formula, f over n. All right, so to calculate each frequency, each probability, we use that same formula for probability, which is f over n. Now, n, we said, is the sum total of all these values. All right, so if you sum total all the row values and all the column values, it's 1164, right? And that's going to be our n. All right, and that's going to stay unchanged. For every probability calculation, we are going to use 1164 as our n, as the denominator. All right, only f is going to vary. So in order to find the probability, all right, in order to find the probability of a person who is under the age of 30 and a full professor, is going to be, how many cases do we have? How many ways can we get somebody who's under 30 and is a full professor? Two ways, right? That's what F represents. That's what F is about. F is about how many ways can a certain situation occur. And this is joint probability that we are trying to calculate, because we are referring to two variables. How many, or what is the probability of finding someone who is under 30 as well as a full professor, under 30 and a full professor? All right, and that number is 2, so you're going to say 2 over 1164. So 2 over divided by 1164 is going to give us 0.002, and that is what you see as the probability. So the probability of finding somebody who's under the age of 30 and a full professor is 0.002. How did we get that? 2 divided by 1164. The probability of finding somebody under the age of 30 who's an associate professor, that means A1. Again, let's use the notations that have been given to us. This is the second one, is the probability of A1 and R2. The first one was the probability of A1 and R1. All right. Then it's A1, A1 and R3. So that's how it's going to go. We can use our uh, the events also, I mean the notation of the events to represent these probabilities. So how did they get 0.049? It's 57 divided by 1164. All right, so all these frequency values are going to get divided by 1164. That's not going to change, 1164. Okay, 52 divided by 1164 gave us 0.045, this value here. That means the probability of finding someone or selecting someone who's in the age group 30 to 39 and a full professor is 0.05. How do we get that? 52 divided by 1164. All right, so we have to go through each and every cell inside this box here to calculate the probabilities. All right, take your frequency or contingency table, whatever the frequency value is that represents F. N is the total sample size divides. It's very simple arithmetic. All right, it's not any high uh, high level algebra that we are performing, but you just have to understand what we are working on and what we are talking about, what everything means, in other words. Now, these values here on the margin, all right, these are called the marginal probabilities. And let me write that down now. All right, all these values here along the margin represent marginal probabilities. Just like we had marginal frequencies, we will have marginal probabilities, and the values inside the box, all right, all these values here inside the box represent joint probabilities here, joint, all right, joint probabilities. So what does this 0.058 mean? 0.058 is the probability of finding somebody or selecting someone under the age of 30. And that's it, only age, all right? Because this is marginal, it does not talk about joint probabilities, all right? It won't talk about two variables together. It's just the probability of finding somebody under the age of 30, irrespective of what rank that person is. What is the probability here? 0.275. What does this mean? 0.275 is the probability of finding an assistant professor, regardless of the professor's age. All right, it's the if somebody asks you what is the probability of selecting somebody who is an associate professor, 0.327. So for those values, when they mention only one variable, it's you have to look at the values along the margins, the probability values along the margin. If they refer to two variables, then you have to refer to the values within the box, inside this bold rectangle box, right? So that's what joint probability and marginal probability means, and that's how you calculate your probability values. All right. We'll now talk about a very important topic in probability, especially when we deal with joint probabilities or probabilities of two events. It's called the conditional probability. Now, let's read what it is about, and then I'm going to be explaining it a little bit. The probability that event B occurs given that event A occurs is called a conditional probability. It is denoted by the notation P, then within brackets we have B, and then a vertical bar, and then the letter A. So the two events are A and B, and the way we read it is the probability that event B occurs given, this vertical line implies given that A has occurred. All right, so probability that B will occur given that A has occurred, which is read the probability of B given A. So this line here, the straight line, vertical line, is to be read as given. We call A the given event. So the given event in the notation, the given event is written last. All right, the first one is the event that is about to occur, and the given event is the one that comes on the right hand side of the straight line, right? Now there's a formula to calculate the conditional probability. If A and B are any two events with probability of A being greater than 0, then probability of B given A equals probability of A and B divided by probability of A. Now, probability of A and B, as you can tell, is joint probability, is the joint probability. That means the probability of A and B occurring together, both events happening together, divided by probability of A. All right. Now, again, the condition here is in order to calculate this probability, the conditional probability, we have to make sure that probability of A is not equal to 0. It is greater than 0, because if it is 0, the denominator of this formula is going to be a 0, and that will cause the value to be undefined. All right, that's why they have specified here that P of A must be greater than 0. All right, so now we'll go into some exercises to calculate conditional probabilities. We are going to use this example to demonstrate how conditional probabilities can be calculated. All right, so given here, as you can see, is a contingency table, but this contingency table really gives us the probability distributions, not the frequencies. They have calculated the probability the probability distributions and have shown them on this table. And we have two variables here, right? Contingency tables always deal with two variables. They are frequency tables for two variables. So the two variables here are gender and marital status. The two genders, male and female, are across the rows, and the marital status are along the columns. So we have four marital statuses here: single, married, widowed, divorced, and they have their notations. So the different marital statuses are indicated as M1, M2, M3, M4, and the genders are indicated as S sub 1 and S sub 2. All right, so within the box here we have what's called the joint probabilities, correct? These are the joint probabilities. And in the last column and the bottom row, we have what's called the marginal probabilities, right? So this and this represent the marginal probabilities. So the way we read the joint probabilities is the probability of selecting somebody who is a male and single. Probability of finding somebody who's a female and married, 0.284. That's the probability. Probability of somebody who is widowed, that's marginal. We just said one variable there, the marital status. All right, probability of selecting someone who's widowed, 0.063. So when we want to find the probability of a single variable, we have to look at the marginal values. Whereas for joint probabilities, it should be stated with two variables, right? Somebody who's married and female, 0.28. So and, all right, and suggests joint. Now, the question here is, what is the probability that the person chosen will be single given a female is chosen? So instead of saying single, married, widowed, I'm going to use these notations, M1, M2, M3, M4, and S1 and S2. So the question says, what is the probability the person chosen will be single? That implies the marital status, and that marital status indicated as M1. So I'm going to write it as probability of M1 occurring given. So given is indicated with a straight line, all right, a vertical line. Given a female is chosen. What is the symbol for female? S sub 2. S sub 2. All right, so that's what we have to find. Again, I just want to review the notation. So probability of M1 occurring, which is single, so somebody is single, given a female is selected, S sub 2. Again, the formula is probability of, it would be the M1 and S sub 2 occurring together divided by the probability of the given condition. All right, in the bottom or in the denominator, at the bottom in the denominator, we will have the given event. The given event is S2, the one that comes after the straight line here. All right, so P of S2. Now, luckily, we don't have to calculate the probabilities. It's all given here on this table. So probability of M1 and S2 occurring together, M1 and S2, right? So here it is M1 and S2. This is the value 0.121. All right, so this is the value you should pick for probability of M1 and S2 occurring together, occurring jointly is 0.121. So 0.121, and the probability of selecting a female, right? Probability of S2 is the probability of selecting a female. That's a single variable. All right, we are just talking about the gender probability of finding someone who is a female. All right, who is a female, that's 0.515. For that, we have to pick out the marginal value, so 0.515. All right, and then the calculation is done here. We got a value of 0.2349. Now you can round this up to 0.235. Please do not round to anything less than 3 decimal places. All right, you can round this up to 0.235, but please don't make it 0.24. All right, so all right, so this way we go about finding conditional probability. All right, and we'll go through some more examples in the worksheets. Okay. From the formula of the conditional probability emerges what's called the general multiplication rule. If you recall, the conditional probability had this formula, right? It said probability of B given A was equal to probability of A and B, or probability of B and A, doesn't matter which one you put first, but the probability that both events occur jointly divided by the probability of the given condition, which is A, probability of A. Now, if you solve for probability of A and B from this equation, or from this formula, you will get what's called the general multiplication rule. The general multiplication rule is probability of A and B equals probability of B given A times probability of A. So how do we get this? From the conditional probability rule, just solve for probability of A and B by moving probability of A to the other side. Multiply both sides by probability of A, right? We want to get rid of the probability of A, just like you solve in an equation, right? This is an equation. We're just doing that. So multiply both sides by probability of A, and we end up with probability of A times probability of B given A, And that's what the general multiplication rule is. So if A and B are any two events, then the joint probability of A and B happening together is equal to the probability of A multiplied by the probability of B given A. All right? Now here we are demonstrating the general multiplication rule with an example. All right, so let's look at the application that I will be demonstrating. Let's say in a class is a total of 40 students, all right, male and female together. And the number of male students is 17, and the female number of female students, total number of female students is 23. And I want to pick two students at random from my class of 40, right? And then I want to estimate or understand the probability of the different combination of genders I can get from my two picks. All right, so I'm going to pick two students at random, one after the other. All right, uh, the names of two students, and I want to determine afterwards what is my probability of getting different genders in that, or all possible combination of the genders. All right, so in other words, when I pick the first time, when I draw a name the first time, my first student can be either a male or a female, correct? And in the second draw, I can have likewise a male. I can either have, in the second draw, I can also have a male or a female. All right. Now, what are all possible combinations that can happen from this pick here, this pick here? In the first poll, all right, in the first draw, I can either get a female or a male, equally likely occurrence, all right, equally likely event, in other words. So when I draw a name the first time, it could either be a female name or a male's name, all right, male student's name. And then on the second draw, after I pick a female in the first draw, let's say, I can get maybe another female, or I can get a male, right? So what are the two combinations here? If I pick a female first, then in the next draw, I can either get another female, or I can get a male after the female in the first draw, correct? Now, the other alternative is if I get a male in the first draw, all right, then in the second draw, I can get a female, or in the second draw, I can get another male. So these are the complete combinations of genders I can get by drawing two names from my pool of 40 students. Okay, so now I want to calculate the probabilities. Now probabilities will be calculated using the same formula that we used before. Probability equals F over N. So N we know is going to be this 40, the total number of students in the pool from which I'm drawing the names. All right. Now, if in the first draw I pick a female, what was my probability of picking a female from my pool in the first draw? There are 23 ways I could get a female. There were 23 names, in my box, and if I drew a female's name, then it would be 23. Each female student had an equal chance of getting picked, correct? So F is 23 and then divided by 40. Again, we are applying the F over N rule. N is the 40, F is the 23. So the probability of picking a female in the first draw was 23 over 40. What is the probability of picking a male in the first draw? 17 over 40, because there are 17 ways in which I can pick a male student. So F is 17 and 40 is N in the first draw. Let's look at what happens in the second draw. In the second draw, if I picked a female student, then the probability of picking a female student the second time would be 22 over 39. All right, why so? Because that probability depended on the probability or the event that occurred previously. Because we picked one student in the first draw, my total pool is now depleted by 1. My total pool is reduced by 1, and that's why N has now become 39. What about the F? I had picked a female student in the first draw, so now my pool of female students was reduced by 1, and that's why I have 22 for my F in the second draw. So 22 divided by 39. So as you can see, this probability was dependent on what happened in the previous draw. It became what's called a conditional probability. All right. Given that a female student was drawn the first time, what was the probability of another female student getting picked? All right. So the general multiplication rule helps us, or is based on conditional probability, as we saw before, and it is used when there is one event dependent on a previous event. How about the probability of picking a male student given a female student was picked in the first draw? What happens to my pool of students, the total pool of students? That's 39, because I've already pulled one student from my total set in the first draw. Now I have only 39 students left to pick from. And male students, I never picked a male student before, so that pool was intact. So I have 17 over 39. All right. Now let's look at the bottom part here. If I picked a male student in the first draw, then it was 17 over 40. We discussed this already. What happens if we picked a female student following a male student? Given that a male student was picked in the first draw, what is my probability of picking a female student in the second draw? My N is going to be reduced by 1, of course, 40 minus 1, because a student was already picked irrespective of their gender. But the female student pool stayed intact, correct? It still had 23 students, so 23 over 39 is the probability of picking a female student given a male student was picked before. And likewise, what is the probability of another male student getting picked given a male student was picked before? 16 over 39. Why 16? Because a male student was picked, so my pool of male students was reduced by 1. So that 17 became a 16, and in the second row my total pool also got reduced by 1, so I have 39. And now to calculate the joint probabilities. And here are the events F1 and F2. F1 followed by F2. You have to multiply the two probabilities. That's why it's the general multiplication rule. So 23 divided by 40 times 22 over 39 is 0.324. 0.324 is the probability of picking a female student followed by a female student with these numbers, with the total number of students being 40, number of male students being 17, number of female students being 23, and so on. All right, so in order to calculate these joint probabilities, uh, you have to multiply, you have to use the multiplication rules. All right, F1 and M2, M1 and F2, M1 and M2. Okay, so again, to summarize, the general multiplication rule is used when the probabilities, when the events, successive events are dependent on what happened previously, what event occurred previously, and then to calculate the combination of events, you have to multiply the two probabilities, not add like in the special addition or general addition rule. You have to multiply them. All right. We are now going to discuss the differences between dependent and independent events, especially in terms of their probabilities and their calculations, right? So dependent events is what we just talked about with the general multiplication rule, where one event or a certain event is dependent on what happened in the previous event or in the previous trial, so to speak. All right. So we are going to use the same example that we discussed previously for the general multiplication rule. We have a pool of 40 students, out of which 17 are male and 23 are female, and we are going to draw two students in succession at random and determine the probabilities of all possible combinations of genders in the two draws. All right. So we said that in the first draw, we have an equal chance of picking a male student or a female student, right? So in the first draw, you can get either a male student or a female student. Now, the probability of picking a male student in this case would be, the probability would be, remember F over N rule. N is 40 in the first draw, all right? And the number of male students was 17. So there are 17 ways in which a male student can be picked. So it would be 17 over 40. Now, the probability of picking a female student in the first draw would be 23 over 40, correct? Because there are 23 ways in which we can get female student out of a total of 40 students, right? Now, after we complete the first draw, our total pool of students change, and so does the number of male or female students, depending on what was drawn in the previous trial. All right, so after a male student was drawn in the first trial, again we have an equal possibility of picking a male or a female. However, the probability of picking a male student, given that a male student was drawn in the first trial, would be 39 in the denominator and 16 in the numerator. Why so? Because in the second draw, we've already pulled a student, right? So that 40, the total number of students in the second row, would be 39. All right, because we've pulled one student out and we are not replacing that student back into the pool. So it's going to be without replacement. Therefore, our total pool gets reduced by 1 to 39. And what happens to the male students, since we've already picked a male student in the first row and the second row, the pool of male students will be one less, which is 16. All right, so the probability of picking a male student following a male student is 16 out of 39. In the second row, what is the probability of picking a female student, considering that we picked a male student before? The bottom line would be 39. The denominator would still be 39. However, the number of female students would still be intact as 23, right? Because in the first draw, a male student was drawn, so the number of female students didn't change. So in the second draw, we have 23 ways in which we can draw a female student. So it would be 23 over 39. All right, so for considering that a female student was picked in the first draw, in the second draw we could pick either a male student or a female student, correct? What would be the probability of picking a male student given a female student was picked in the first draw? It would be 17 out of 39, right? 17 out of 39. What is the probability of picking a female student given that a female student was picked in the first draw? It would be 22 over 39. Why 22? Because since we already picked a female student in the first draw, the number of female students was reduced by 1 in the second draw. All right, so it's now 22 over 39. And if they ask you to find the probability of a male and a male, so it's 17 over 40 times 16 over 39. If it's the probability of picking a male student followed by a female student, it would be 17 over 40 times multiplied by 23 over. So we just multiply the probabilities, but it's important to figure out the probabilities at each trial correctly in dependent events. What happens in independent events? The example that I'm going to follow or I'm going to use to demonstrate independent events is the gender of babies being born. All right, so think about it. In the first birth, we have equal chances of a male child or a female child. All right, equal chances. Somebody could have a male child or a female child with equal probability. So what is the probability of getting a male child in the first birth? Since the total number of genders is 2, our n is 2. Gender is equals 2, correct? Male or female. So the probability of having a male child is 1/2 in the first birth. The probability of having a female child at the first birth is also 1/2. Now, given that a male child was born at the first birth, what is the probability of having another male child in the second birth? The same probability. All right, it's still 1/2. Just because somebody had a male child in the first birth doesn't change the probability of having a male child at the second birth. All right, given this example, given this situation. So in this case, the probability does not change. The probability at a particular trial does not change based on what happened previously. All right, what is the probability of having a female child after a male child? That's also 1/2. All right, and same thing, what is the probability of having a female child following the birth of a female in the first birth? Is 1/2. And same thing, male followed by a female is also 1/2. So in this case, in this example, what is the probability of having male followed by a male, 2 boys, is 1/2 times 1/2, all right, which is 1/4. What is the probability of having a male child followed by a female child? It's 1/2 multiplied by 1/2, which is 1/4. All right, so note the difference between independent and dependent events. In independent events, what happens at a particular trial is not determined by what has happened in the previous trial. All right, the probabilities at each trial remains the same for independent events. For dependent events, as you can see, the probabilities changed based on what happened in the previous trial. Okay. We are now going to read through the definition of independent events. It says the outcome of one event does not affect the outcome of another event for independent events, right? We saw that example of genders at birth, the likelihood of having a boy child or a girl child at successive births. Event B is said to be independent of event A if probability of B given A equals the probability of B. That means the probability of an event is not affected by the given condition. All right. The special multiplication rule. So far we studied the general multiplication rule that applies for dependent events. Now we're going to talk about the special multiplication rule for two independent events. So if A and B are independent events, then the probability of A and B equals the probability of A times the probability of B. And conversely, if probability of A and B equals probability of A multiplied by probability of B, then A and B are independent events, right? How to mathematically determine if two events are independent. Now, event B is said to be independent of event A if the probability of B given A is equal to the probability of B. Therefore, to determine if A and B are independent events or not, we first have to calculate the probability of B given A, so the conditional probability of B happening given that A has occurred, using, remember the formula for the conditional probability, it's probability of A and B divided by probability of A. And then we also have to find the probability of B. What is the probability of B occurring on its own? And then we compare the two values, the value obtained from this calculation, the conditional probability, and the value from the probability of B. And then if they are equal, then the conclusion is that A and B are independent events. Now I'm going to work through this problem just to get some extra practice on how to calculate different probabilities and also compute the conditional probabilities as well as decide if certain events are independent or not. So the problem is about a balanced dime being tossed 3 times in succession with all possible combination of outcomes. So 8 equally likely outcomes are possible. When a balanced dime is tossed 3 times, 8 equally likely outcomes are possible. And these are all the combinations that you can get. You can get head, head, head. So all 3 tosses could give a head, or you could have a head in the first toss, tail in the second toss, and again head in the third toss. Or you can have a tail at the first toss, then a head and a head in the 2 other tosses, then T, T, H. So these are all possible combinations of tossing tossing a coin 3 times. All right. Now these are the events uh, denoted by A, B, C. The first A is the event. The first toss is heads. Event B is the third toss is a tails. And C is event the total number of heads is 1. So in the total number of heads is 1 means that you get only 1 head out of the 3 tosses. So let's go through the questions and calculate the probabilities. Probability of A, what is A? Event, the first toss is heads, all right? So how many total combinations do we have? 8, right? So again, we are always using the F over N formula. So our probability is going to be calculated with the F over N formula. N is going to be 8 because we have 8 equally likely outcomes. And then for probability of A, what is A? A is, just a second, I'm trying to pull up my pointer here. I don't know why it's stuck. Okay, so event the first toss is heads, all right? So out of these 8 combinations, how many ways can we have heads in the first toss? So this combination has heads in the first toss. Then this one has heads in the first toss. This one doesn't. This one doesn't. But the fifth one has H in the first toss. So there are 4 ways in which we can have heads in the first toss. So F is going to be 4, which is 1/2. So probability of A is going to be 1/2. What about probability of B? So let's go back and read what probability of B is. The third toss is tails. The third toss is tails. Again, N is going to be, all right, so again, it's the F over N rule. N is going to be 8. So we have to find how many ways we can have tails in the last toss, in the third toss. So there's no tails here. This one doesn't have a tail in the third toss. This one doesn't either. This one doesn't either. Now, this one, HHT, has tails in the last toss, third toss. So does this one, so does this one. So there are 4 ways in which we can have tails in the third toss. So it's going to be 4 divided by 8, which is also 1/2. Again, you always have to convert this to decimal, so it's going to be 0.5 for probability of A, 0.5 for probability of B as well. All right, now probability of C. So what is C? It's the event the total number of heads is 1. The total number of heads is 1. Again, F over N rule. Again, the total number of outcomes is 8, right? So out of that, in how many situations do we get a total number of heads as 1? This one has 3, total number of heads is 3. This one has total number of heads 2. So does this one. This one here, this one has heads as 1. This one doesn't, but this one does. This one does, right? So 3 out of 8. There are 3 ways in which we can have a total number of heads as 1 in 3 tosses. So it's going to be 3 upon 8. Okay, 3 upon 8, you have to find what the decimal value is. All right, now this one here says compute B given A. All right, so probability of B given A would be, again, let me just see what each of these means. B is the event, the third toss, third is tails, and A is the event that the first is a head, correct? So probability of B given A. Now, what is the formula for conditional probability? It would be probability of B and A happening together, the joint probability, divided by the given probability, so probability of A. All right, so what is the probability of A? That's easier to find, right? That's 1, we calculated it here, right? So there are 4 ways we can get heads in the first toss out of 8, correct? So I'm going to write here 4 divided by 8 for probability of A, right? Probability of B and A. So how many situations do we have where the first toss is heads and the third toss is tails? So first toss heads, and the third toss tail. So let's go over it. This one doesn't even have a tail. This one doesn't have. So first head, last tail. First head, this one is, right? HTT. So this is one of them. Anywhere else that you have? First toss is heads and third toss is tails. First toss. This one too, right? This one as well. HHT. HHT and HTT. None of the others have first heads, and so it's going to be 2 out of 8. 2 out of 8. So out of 8, we have 2 cases where we have H for the first toss and tails for the T for the last toss, the third toss. So now you have to do this fraction division. 2 divided by 8 divided by 4 divided by 8 would be how much? What do you have to do to divide fractions? 2 divided by 8. Remember how you divide fractions? You change the division to a multiplication and flip the fraction in the denominator. So now you write it as 8 over 4, which is 2/4 or 1/2, right? 1/2. So 1 divided by 2, half. How about compute probability of C given A? So what is C? All right, C is, well, first let's write the formula here for the conditional probability. It would be probability of C and A occurring together divided by the probability of A. That is, so what it says is, what is the probability of the event that the total number of heads is 1, given that the first toss is a heads? All right, so first we have to calculate the numerator, C and A. That means the probability of having the first toss as heads and the total number of heads as 1. All right, so let's look at how many situations we have with H as the first toss. We just have these 4, right? These 4 have heads in the first toss, so we narrow it down to that. Out of that, in how many cases do we have 1 heads? In only 1 case, correct? Only in this case. So probability of C and A happening together is 1 out of 8. All right? It's 1 out of 8. Where we have the first toss is heads and just total number of heads is a 1. And then divided by probability of A is 4 over 8. So now we do the division again. 1/8 multiplied by 8 over 4, again fraction division, which is 1/4, which is 0.25, right? This one is 0.5. Now, for the next one here, it says are A and B independent events and why? Okay, so to find whether A and B are independent events or not, we have to use this formula here. This probability of A given B equal to the probability of A. Okay, so probability of A given B, did we find that before? No. So what is the probability of A given B? We have to find the conditional probability first. Probability of A we know is this one. We know is, what is it, 1/2. So if probability of A given B is also 1/2, then we can say they are independent events. Otherwise, they are not. So let's calculate probability of A given B. Again, the formula is probability of A and B occurring together divided by the probability of B, right? So probability of A and B, we calculated that somewhere before. B and A and B, same thing. So that was 2 over 8. And probability of B was 4 over 8, which is 1/2, correct? When you do this, we should, it should be 1/2. So probability of A given B is also 1/2. So we can say they are equal. Okay, so they are independent. Why? Because the probability of A given B is the same as the probability of A. All right, so you should be able to now work out the last one, are A and C independent events or not, and answer the last. I'll leave it to you to complete the last one. Okay.